Our network predicted 0.78, but the true answer was 1. So, how wrong is that? To train, we need to turn that mistake into a single number. That's the job of a loss function. The prediction was 0.78. The truth was 1. So it's off by 0.22. A loss function takes that gap and turns it into one number, and that single number is what training will try to make as small as possible. The simplest loss is mean squared error. Take the gap between the true value and the prediction, and square it. For our prediction of 0.78 against a target of 1, that's 0.22 squared, about 0.05. Plotted across all possible predictions, it's a smooth bowl. This is the usual choice when you're predicting a number, regression. For classification, where the prediction is a probability, we usually use cross-entropy instead. When the true answer is 1, the loss is minus the log of the predicted probability. For 0.78, that's about 0.25. Notice its shape. As the prediction drops towards 0, the loss shoots upward. It gets very large when the model is confidently wrong. Here's why that matters. Suppose the model predicts 0.1 when the true answer is 1, confident, and badly wrong. Mean squared error calls that 0.81, but cross-entropy calls it 2.3, and it keeps climbing toward infinity. That steepness gives the network a far stronger push to fix confident mistakes, which is exactly what you want when predicting classes. So the rule of thumb is simple. If you're predicting a number, a price, a temperature, use mean squared error. If you're predicting a class, use cross-entropy on the predicted probabilities. Match the loss to the task. In PyTorch, each loss is a ready-made object. Mean squared error loss for regression, cross-entropy loss for classification. You call it on the prediction and the target, and it hands back the loss number. To recap, a loss function is one number telling us how wrong the model is. Mean squared error for regression, cross-entropy for classification, and cross-entropy comes down hardest on confident mistakes. We have a loss. Next, how the network actually lowers it, backpropagation.